Okay, good morning. So today we'll talk about errors. There are two types of basic errors that we will face in this course. Uh, One of them arises from the fact that we use a finite memory for storing data and information on numbers. And the second arises from the fact that we demand from the computer to do a partial calculation, not a full calculation. So the first one is called round-off error, and the second is called truncation error. Basically, you know the two errors by yourselves, but now we will get them names and we'll play a little with them so we can understand how they can affect the results that we want. Basically, we want exact results, but because of what I said right now, we don't have the exact ones, but we have approximate results. But the question to be asked is how much is this result close to the wanted result or to the desired one. So for these calculations, you know that we know how to perform them, and these things are in fact symbols to something that is in our mind, abstract mathematics or mathematical analysis. So I think you are so familiar with the 1 and 2 and 8 and 4, and less familiar with this where it's root of 3, but of course familiar. But what is this square root of 3? It is what we write here is only a symbol. What is this? Okay, you define that in calculus or in mathematical analysis. So you or we assumed by piano axiom that there exists such a set called natural numbers with piano axioms, and from that set we built a set called rational numbers Q, and from that set we built using the Dedekind cuts, we built the real numbers. Okay, so this square root of 3 is actually a couple of two sets that are partition of Q with some conditions, if you recall that. And after we build this or these real numbers, we define what is the addition in that set, and what is the subtraction, and what is the multiplication and division. And we know this square root of 3 as a symbol, and it symbolizes something that is in our mind. We know what it is, but we don't have anything other than this square root of 3 to symbolize it. But we also in calculus knew that there is an infinite decimal representation or decimal expansion of this square root of 3, and there is a bijection between decimal expansions and real numbers if we remove or do not take into account the cases of 0.99999 or infinite nines in the last of the number. Because of that bijection, we know that there is an infinite expansion for every real number. But we always take some amount of these digits to the top, and we say that the error is so small and I do not care for it. That's in the decimal representation. And of course, there is also a binary representation for each real number, and this is also infinite. But when we use computers, we have a finite number of bits to store the information in. And why do we use bits? Why don't we use actual signals in the computer which are continuous and use them? And then we have real numbers because the voltages and the currents and the analog circuits in the computer are in fact continuous, I guess. So why don't we use these continuouses? Hmm? No. Noise, yes. So if I want a real number, if there is some noise in the system, I lost that number. And the bits are much, much, much less sensitive to noise than this representation. Yes? So if I take the one to represent the case of the voltage or the current to be above some cutoff, to be above some cutoff or or some threshold, this is the one, and the zero is when the voltage or the current is below some value, and this is the zero. So this is much strong and robust against errors or against noise from using the analog value of the signal. So we have bits, okay, and we can represent values with these bits, and there is a finite number of bits, and we have standard or typical ways of storing the values. The first one called float. And this float uses 32 bits to store a number. And the second is double float, or let's call it double. And I talk here about rationals, yes, rational or real numbers with decimal expansions. When we talk about integers, if we want to store an integer, we have, how do we do that? We take its binary representation with a positive or negative sign, yeah? So the first bit will tell me if the integer is positive or negative, and the other bits will tell me what is the value of that number in binary representation. That's the integers. But floats, we use for them, or real numbers, we use for them 32 bits or 64 bits, where these bits, not all of them represent binary way, the number itself. We widen the range of numbers that we want to be able to store by assigning some of the bits to give another meaning, which is the magnitude or the order of magnitude. Yes. So when we have a float, we store in these 32 bits. We store in the first bit what is called the sign. We store in another 8 bits what we call the exponent minus the bias. And we store in the left 23 bits what we call the mantissa 1 plus 1.m. I will explain this, which is the mantissa. The m is the mantissa. So here we have the number itself, like that. Here is the number itself, and here is its order of magnitude. I will write down what is the number. So in this representation, if you have 32 bits like this, let's say 1 0 0 1 0 0 1 1 1 and 1 1 0 0. Okay. So let's call these bits E0, E1, E7. And let's call this M1, M2, till M23. So the number itself will be -1 to S to the power of S times 1 point M binary. I will explain what is this. Times 2 to the exponent or to the power E minus 3. Okay, and now I will explain. You see? Oh. So the 1 point M actually is 1 plus the sum of mi times 2 to the minus I or half to the power of I. So that is the number. Okay? It's like the decimal representation. So when you have 1 point something decimal representation, what is this number? You have this number is exactly this, only the 2 is 10 decimal representation. Yeah. And the E is the sum. So if I call this E0, I can call this E0. Okay? But if I call this E0, the formula of this E is EI 2 to the 7 minus I. I goes from 0 to 7. Okay. So what I write here is for float. You don't see for float. Okay. So if I don't have minus b, what are the numbers that I can store in this thing? Which numbers? What is the lowest number and what is the largest number? Which range? What's the smallest number that I can store in? Well, okay. And I will take this condition also. Here, this string of 8 bits, not all of them are okay. At least one of them is 1, so that this number is bigger than 0. Okay. So the smallest number that I can put is 1 here in the mantissa 1. That's the smallest number, because the mantissa will be all 0, and we have this one. We can think about this one as an external bit that is always on. Okay, this one. And we have 2 to the power of 1 at least. So the smallest number is 2. Okay. Pay attention that this number is always bigger than 1 and smaller than 2. Okay, so this is between 1 and 2. Always the 1 point M is always between 1 and 2. So we chose this way of renormalize a representation of this exponent such that always the information about the value is here, and we have another information of order of magnitude. Okay, so we always, this is the number in sum up. We'll see why I call this is the number basically, and this is another information. We'll see that in a bit. Okay. So if we don't use the minus b, the smallest number that we can put here is 2. And it's not good. We want to be able to store also small numbers. Yes?
Sorry, but ones of n is not bounded by 1 and 3, because if we
No. No, you have here half, the first one, half, and then this is always 0 or 1.
okay, but if n I is always 1, and
So you have then 1 plus half plus this plus.
so if we will treat 1/2, etc., as a geometric series, don't we get something close to 3?
No. This is close to 1. This converges to 1 and plus 1 is 2.
How can the lowest number represented by this thing is 1? Because
No, 2, the lowest.
okay, so 2, but we have the sign bit, so it can be minus.
No, I'm talking about the magnitude,
Oh.
the lowest number in terms of magnitude.
Oh.
Okay, so another way we can say that we can, in this way, we can store numbers which are bigger than 2 or smaller than -2.
Yeah, okay.
But I also want small numbers in terms of their magnitude. So we add this minus b, and in floats, the b, it is an offset and bias. The b is 127, and in this way, we can see that that the e minus b goes from minus 126 until 127, and in this way we can store numbers of magnitude or order of magnitude of 2 to the minus 1. Okay. Another way we can say that the string of these 8 bits is an integer which can be positive or negative. Okay? And we can say somehow that it is equivalent to a string which the first bit in it assigns the sign of that. Okay? So that's the range that we can cover in 8 bits. And if you have a string of bits 0, 1, 1, 0, 0, its meaning is that number. Okay, any questions? And this is for float. For double float, we have 64 bits. The first one is for sign, and for the exponent minus bias, we have 11 bits in double float. And for the mantissa, we have 52. The sum is 64. And the bias is, of course, because it is being 11, the bias is 1023. And that's how we store the information or the numbers. Any question for that?
Can you explain again the bias?
Okay. Why do I use the bias? I use it in order to be able to store also small numbers as I can store large. How I do that? How do I do that? I fix a number called bias. I know the bias is 127, and I tell you that if I give you a string of bits like this, the number that I represent by this string, you can calculate it like this, where the b is 120. And if I give you this way of getting the number, you can see that you can cover numbers from small as 2 to the minus 127 up to large as 2 to the 120. Okay. Without this bias, if this b is 0, it's it's between us. I tell you that the B is 127. It's a convention. Okay, it's a convention for float that the bias is this. And if the convention is that the bias is 0, so that means that I can only store numbers that go from 2 to numbers that large, like 2 to the 100, 2 to the power of 255. But again, I want to be able to represent small numbers symmetrically as I represent large numbers. Oh, so what about the error? If I represent a number in this way, again, a real number has infinite digits or infinite bits. Okay, but I use only, for example, here, use only 23 bits. So what is the error that can arise from only the storing if I know well what the number is? Oh, yeah,
The relative error is going to be,
not the relative. I ask a simple question. If I make storing like this for a number that I know what it is. Okay, I know what it is in real numbers. For example, square root of 3, you know what it is in real numbers. You don't know how to write it infinitely because you don't have that. But a priori, you can. Okay? You know what is square root of 3. So what is the error that can be in such a story? Example, the question is so easy. You know what is pi, yes? Somehow. Okay. And I ask you to write this pi up to the 8th digit after the point. Okay. So you write for me 3.14. You try to calculate pi by some way from calculus that you know, and you fill these digits. So when you give me this number with 8 digits here, what is your error? Only the last one. Yes? That's because you know how to calculate this pi, and you know how to bound your error, and you know the digits themselves, so you can be wrong only here because you lost the digit here. So your error here will be up to 10 to minus 8. And we say that the error is 10 to the minus 8 because we take the worst case.
isn't it divided by half? Isn't it divided by half? Because if it's,
Not necessarily, because we don't know what is your way of taking this round. Is it by rounding as you think right now, or is it by cutting?
but in binary, it's very easy to do the rounding. Just calculate one more bit. If it's 0, you go down. If it's 1, you go up.
Also, listen, you think about 2, I think about 10.
Right, 5.
The same.
Right? You just calculate one more digit.
Yes.
To do proper rounding.
Yes. Okay. So
So, if you do proper rounding, the error is divided by half. Because it can be up to 1/2.
yes, but that if you calculate that, but we don't calculate it. We store only up to this bit, and I don't calculate it. Okay? So again, if you know that you did the rounding as you think, it's okay. So take that out. If you don't know, take the worst case. Okay, and you'll see that we will be interested in magnitude, in order of magnitude. You'll see immediately that we will be we will throw many constants. Okay, so like here, because it's 10 to the minus 8, what's the error that can be here? It's always only in the last digit. We assume that we will not get an error here in the exponent because we know what's the magnitude, what's the order of magnitude, and we can only be wrong only in the last bit here, which is here, and what is value. So what is the error? Exactly. So the error in storing a float, the error is the same. This no error, this has no error. We assume that we know the sign, we know the order of magnitude, and the error will be only in the last digit. Okay? And this is in binary. So this is 2. This is 2 to the power of minus 23, but multiplied by something. Okay? That's the error of the value. But what do I mean, the error of the value? I mean, if I have an exact value and I want to assign it in such a string, the error is exactly this when here is the sign of that number, and here is the right exponent for that number when it's represented in this way. Okay? That's the absolute error. So what is the relative error of that number? The relative error, okay, so that's the error itself, and I much prefer a f computation minus f exact, not f exact computation. And the relative error, which is the error relative to the value itself, exact value, is the error divided by that value, and you see how these cancel, and we are left with the 0.0001 divided by 1 point mantissa, and the 1 point mantissa is a number between 1 and 2, and worst case is 1. So we take the error, here another half. So we take the error to be bounded by a by 2 to the minus. That's the relative. Okay.
You know, they don't always have the same sign as the actual number.
Yes. Oh. Any question?
Saying the error, like, we could calculate a smaller error, but we know that in general the error is smaller than the size.
Okay.
Like, in this case,
That's the rounding error.
the rounding error,
When I want to store a number in the
it depends on the number.
if I know the number, yes. If I know the number.
In general, there is a largest value.
What do you mean?
There is like, I know the error is bigger than. Which kind of error is it again?
This is the rounding error. I only have a number which I know what is theoretically, and I want to store it in the computer in 32 digits, bits, sorry, or 64 bits. Again, when I know what is the theoretical number. So we are in the very, very, very simple case. Yes.
N's are only 1 and 0, or it's fine.
What?
N can be only 1 or 0.
Yes, it's a string of zeros and ones. All I have here are zeros and ones, including the mantissa, including the I and the giving us bits. We store here bits, and we store here bits, and we translate in our language these bits like this. You can ask me how the computer knows how to add some number to another number. if it doesn't know that this is this number, okay, we have a code. Someone has done a code for that to make the sum between zeros and ones. The computer doesn't know what these zeros and ones represent. We ask it to make manipulations as we exactly want and manipulate these numbers so that it can give us what we want. And also when I say to him or to it, prints x, and it prints x for me to be 70 plus 8. What is this 70 plus 8? It doesn't know. It's a picture for him that he knows that he will present by some code that I told him what it is, or someone told him how to move from here to this on the screen. Okay? Doesn't know that this is 17.8. Another question? Okay. So that's the relative error. So what is the and 2 to the minus 23 is 10 to 10 to what? Minus 7, yes. So we expect in the mantissa in decimals or decimal representation to be an error up to the 7th digit after the 1 plus, the 1 point. And this is the relative. And what is the, because of this, I say the mantissa determines the relative error. Yes. Only tell me that the mantissa is 23 bits, and I know what is the relative error. The relative. But what is the error itself? The absolute error of a given number. The relative error is 10 to the minus 7. If I store the number that is equals to 1, that equals to 1. What is the error? 10 to the minus 7. But if I want to store the number 100, what is the absolute error in that storing? 10 to the minus 5. Yes. Okay. And if I want to store the number 1000, my absolute error in that storing is 10 to the minus 4. Okay. So here we have an example, a simple example for storing in float, in double float. And let's write here what is the way of calculation of the number. So in double, we have here the same equation, but here we sum up to 52. Here we have up to 10. And this is 10 here. This is 1023. And here we have 11, 10. Okay. So here's a string. Again, the computer sees a string of these bits without the coloring that you see. Okay. We know that this string represents a number that is minus 1 to the power of 0, which is plus 1, times the exponent represented by this, we can calculate it, times the 1 point mantissa represented by this, we can calculate. How do we calculate it? So the exponent is 1 times 2 to the power of 10, plus, all of these zeros, they don't contribute. And here is the number 3. You remember that, yes? 11 is 3. And so it is 1027 minus the bias. The bias is 1023. It is 4. So we have 2 to the power of 4 multiplied by plus 1 multiplied by 1 point. The mantissa. What is the 1 point mantissa? It is 1 plus. Again, this one is always on. It's 1 plus something What is the something? 1 multiplied by half to the power of 1. So we have the first, the third, the fourth, the fifth. So we have 1, 3, 4, 5, and the 8. Okay, so here's the 8, and after that the 12. And that is the number represented by this. Is it the only number represented by this? No. If we want to represent this number that we know, okay, this number you know what it is. Yes. If you want to represent it in the double float, its representation is this, okay. But also, if I want to represent a very, very, very close number to it, I also will represent it like this because I don't have enough digits or enough bits. But how much very close? We know the answer. How much very close? Close up to 2 to the minus 55, 58. Okay. So, in terms of the bits, what are the two close numbers to it? Two closest numbers. It's only changing the last bit. Yes? It's only changing the last bit. So 1 up and 1 down. If we add to this 0, 0, 0, 0, 0, 0, 1, or we subtract from this 0, 0, 0, 0, 1, these two strings are there. Are the representatives. So numbers between this and this, the computer might store them as this. Why do I say might? Because it might store them also, it might store it like this, okay? But I know that my error is bounded by the 0, 0, 0, 0, 0, 1, and these two numbers in our decimal representation are these. So any theoretical number between or in this range, I will store it as that string that is so. Okay, and you can see that this is a very small range because it's only starting from the 7th or 8th digit, it starts to change. So that's my error also, I know. Okay. Any question? Okay. So first, if we want to store a number that is smaller than the smallest number, it is not a problem. We can store it as 0. This is what's called underflow, but we have to pay attention if our problem, our mathematical problem, we have to understand our real problem or actual or physical or engineering problem. We have to know before that that this small number, I can't treat it as 0. Okay? There are many problems that very, very, very small numbers can affect them in a large way. Yes? So we have to know somehow our background or our mathematical background in order to say, okay, it's okay to take these small numbers as zeros. Okay, that's first. And if I have a number that's bigger than the largest number I can store, that's the problem of overflow, and the program will stop and say to me, there's an overflow, I cannot continue unless I manage that in the code that if something like that, okay, but basically it will stop. Program will stop because of that problem. And again, this error, which is the round off error, is an error of the machine. An error only because you gave me a machine, which and you told me that that I can store the information or the values in a float way or float type or in a double type, and I cannot change this error. Okay. this error might change with its propagation in the code, yes? Because I do many calculations, so this error might change. It may probably it will be bigger than it was, yes. But I mean that this error a priori, the random error, when I want to store something, I cannot do anything with it. It's by the machine. It arises, or it's a consequence of the fact that I use only 23 bits for storage. I cannot do anything with this. And the second error that we will talk about is the truncation error, and this I can do something about it. And it depends on our mathematical techniques or abilities. So what is the truncation? So we finished the first one, and here is the truncation. Truncation error is a consequence, or it arises from the fact that I demand from the computer to do not a full calculation for something. So something has to be done with infinite steps, and I tell the computer to do it with finite steps. So it is not related to the memory being finite. I can have finite memory and demand an infinite calculation somehow, and I can have an infinite memory and demand a finite calculation. Yes. An example for this is integration. You know, how do you make an integration numerically? Basically, you know how to do that. You take small steps of the function of the x axis, and you find what is the what is the area of each rectangle, and add them. If you want to be more precise, so you take smaller steps, okay? So the integration is in fact integral. Somehow we infinitely sum differentials, but how do we do that? Numerically, we do it in finite steps, and because of our mathematical background, we can also know how much our error in this calculation is in terms of bound, in terms of a bound. Okay, so that's maybe a big example. So let's start with the simplest example that you know, and this example you know very well. If I want to calculate this the sine of x, how do I do it? So if you know, or remember from other courses, how does the calculator or computer can do this sine? The answer is, that there are basic circuits, digital circuits with transistors. You know that, okay? And there are zeros and ones. I can represent numbers as bits, and I can define some gates and an OR. And after that, I can somehow build a circuit that can add two numbers. And after that, I can build a circuit that can add and subtract numbers. And after that, I can build a circuit that can multiply numbers. But how do I make sine? The answer is, if my computer or calculator wants to represent the answer up to the 10th digit, so I take, for example, the first 20 terms in Taylor series of sine, and that's basically multiplication and addition that I can do. Okay. So that's how computer does this. And the question is, okay, what is the error when you do this finite calculation where we know that the sign is the infinite sum of sums? Okay. So let's talk about general function f of x, and let's assume that it is smooth and differentiable infinitely or infinite times. So we know that if it is what's called analytical, which means the Taylor series does converge to it. So the function itself equals this until infinity. Okay. But what happens if we want to do the sum until an natural number n, and to stop there, to cut the sum there or to truncate there? The answer is okay. The f of x equals this polynomial plus an error or remainder. And thanks to Lagrange, we know what is this remainder in terms of the n plus 1's derivative of f. Okay? But it is calculated not in x itself, so in x0 itself, no. It is calculated in some psi between x0 and x. Okay? You remember that? It was in calculus. That's called the Lagrange remainder. And this remainder, we hope, and most of the times it will, we hope that it converts to 0 when n goes to infinity. Yes. So this equality or equation is exact. Okay. But we can say this function, because we know it mathematically, we can bound this number, and then we can give a bound, a general bound of the of this remainder. Okay, so let's see that. And in a simple a simple example that you know already know. So if I want to make this expansion around 0, so x minus x0 is x itself, and we call it h. In this course, we will call this very small step that we will do, we will call it most of the time h. And here we make this step one time, but we will see in the next weeks that we take h to be one step from very, very many steps. And we know that the sign of h equals this infinite sum. And we can say also it equals h plus the third derivative of the sign calculated in some number between 0 and h divided by 3 factorial multiplied by h cubed. Okay? And now we know that this number is, in its magnitude, it's smaller than 1, so that the error in its magnitude is smaller than h cubed divided by 6. So for large h, this is not so good. For example, let's take h to be 10. So the sign of 10 equals 10 plus minus 200, maybe. It doesn't mean anything. But if h is 0.1, okay, the sign of h is 0.1 plus or minus 0.1 cubed divided by 6. Okay. That has a meaning, so the error is small. And here's the error. The truncation error is h cubed divided by 6. And we are so interested in the behavior of the error, how it behaves, how it depends on h. Okay, so we many times don't care of this constant. So we say epsilon is smaller than a constant h to the power of n, and we can represent this by O of h to the n.
Yeah, but still we know that the sign for the third derivative of sign is between 0 and 1. But what do we do in the case that it is not the sign?
Okay, so first of all, you've seen many, I think, you've seen many problems in calculus that you already solved. If we cannot bound it, okay, we can bound them. But most of the time, with the exercises that we will take, we can bound this function. Okay, so it's mathematics. It's always to make tricks. Okay, maybe you cannot bound this, but if you choose to represent the function in another way, you can. It's mathematics. So you might face a problem with no ability to do that. Okay, but we will not face that. Okay, no, let's take another 5 minutes and then go to a break. Okay. So we have two errors, and the total error of some variable is the combining of the two errors, and we assume in this course that these two errors do not speak with each other, do not couple to each other, do not play with each other. One does not get another one bigger through its propagation. So this is an assumption, and it works very well in our cases, but a priori this doesn't be. It is not necessarily true. Yes, maybe this error when it propagates affect the truncation error, and the truncation affect the round off error. But this is our assumption, and we have seen that the error of truncation depends on some parameter called h. Yes? Not necessarily the same h, okay, that we've seen before, but it depends on some parameter, and the round of error also we assume that depends on h, and we will see an example for that. Up to now you don't see it clearly why it depends on h, and if this is the error, so our hope is to find a minimum of this function and then choose the h according to that minimum. Yes. We want the error to be small as we can. Yes. So the maybe not we want the total error to be small. Maybe this gets big and this gets big, but in the opposite direction with minus. So we don't care. We do care about the total error. We want it to be as much small as we can. And of course, through the propagation, we expect the error to accumulate and be larger. Anyway, we asked about as small as we can. So we hope that if we know this function, we can make a derivative of the total. Okay, and then the optimal h that we choose for our numerical calculation is the h that satisfies this equation. Now in this course we have two optimal h's. You have to be aware of which one we are talking about. So this one is the first, and another definition of optimal h is that these two errors cancel each other. Okay, so that the absolute value of epsilon truncation equals the absolute value of a round-off error. So that's another H optimal or optimal H. And we hope that we find such an H, okay? So for that, or an example for that, let's take the derivative, okay? We want to calculate the derivative of some function in some point x, okay? So the derivative is, we know it's the limit of f of, we took this symmetric way because it's better, but mathematically it's true. It's the limit of f of x plus h minus f of x minus h divided by 2h when h goes to 0. And if we want to ask the computer to do that, it cannot, because it has to divide over small, very small numbers, and we have the problem of a overflow when we divide with what's over small number. So we here it enters our mathematical knowledge and background. So we say, okay, it's hard for him. Okay, so we know mathematically that f hat also equals to this. When this psi is some number between what and what? It's between x minus h and x plus h. We know mathematically that this equation is true when psi is some number that we don't know. It's between x minus h and x plus h.
See the take it out of it.
What?
Well, I go down.
Now? Okay. So we know mathematically that this is true, and we want to use this or to take advantage of this knowledge in order to approximate the value of f of x for small h's now. Okay. And with this, we know what our error is. So if we took that way, we don't know what is our error. Now, with our mathematical knowledge, we can bound our, okay? So now let's take a break of 10 minutes. In these 10 minutes, you try to prove this equation. Okay. Again, what's the question? What is the C? What's the meaning of the C?
The C.
C. Okay. 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 The C is from a previous course, which you have proved in it that if I truncate the polynomial, the infinite polynomial in a finite position n, then I can write what is the remainder exactly in this way when the psi of x is some number. I don't know what it is. It is some number between x0 and x. Okay, so it's like the mean value theorem. Yes, you say if the function is positive here and it's negative here, so there is some point x. I don't know where it is. There's some point x where the function equals 0 if it is continuous. Okay, so in a simple way, you proved Rolle theorem, and then you get to Lagrange, and the Lagrange theorem says there is some point that satisfies this equation. Okay, and this psi is between x0 and x. For example, this psi is a number between x and x plus h, and this psi is a number between x and x minus. I say now that the sum of these two values is the same function calculated in a third number which is between x minus h and x plus h. I don't know what number is. Okay, but it's certainly between x minus h and x plus h if this function is continuous and differential. If the gap. Yes, it's continuous. If that. Okay. So now I want to tell the computer to calculate this, and then I will say, okay, I made a truncation, and this is my error. I can bound this error if I know what is the maximum of this function, what is the global maximum of this function in the range of x minus h and x plus h. Okay. And we see that this is the error. And again, I want to tell the computer to calculate this. But when the computer wants to calculate, it saves or stores f of x plus h. Let's assume that it knows how to calculate f itself. But when it wants to store it, f of x plus h, we have again, well, without again, we have the round-off error. Okay, so we have the truncation error here, but we also have the round-off error here. So so here we have epsilon for the first value that we want to calculate, and we have another epsilon. The first epsilon is an error in this value, and this epsilon is error in this value. So when we calculate the f minus f divided by 2h, we have another error other than the truncation. So this is a consequence of the rounding.
There's also an error in that very same expression. Because then you take those two errors
Again?
like there's an error in the two errors, right? But there's also an error when you subtract, then an error.
That's the error when I subtract. That's it.
Oh, yeah, the value is that.
Huh?
It comes out as good. There's no proof.
If it stores the exact value plus this error, so it will give me this. That's for sure.
No, what I'm saying is that the expression f minus f divided by 2h is itself a function that has additional error because of the two operations, subtraction and addition. Right? When you subtract it,
No, I assume that I know h exactly. I know h exactly, and I can represent it exactly. Okay.
division happens. Okay.
Okay.
Like we assume that's not.
Yes, the division is precise here. If I have this,
If I take 1 divided by 3, it's not going to give me an exact representation of binary. Right? If h.
What? Again,
This is not an operation we do in the computer? Because is this not an operation we do?
it is an operation by the computer. Okay.
We do any operation, go to a number space, you take error.
Yes.
So here you calculate this set, right? Then an additional operation is divide h.
Okay.
And an additional operation is divide by
Okay.
2h.
Okay. That error, you want to add another error of the bit. That's it. The last bit, yeah? Okay. Okay. So basically it's the true thing to do. Yes. Okay. But because that I see this now, I see this divided by 2h, I can say probably your error will not affect because this is the bigger error. But I have to say probably. So again, the true thing to do is what you say. Okay? And I will explain why. Here it is. So again, we have two errors. And let's take the optimal h to be the h that makes this equal to this. So that the total error is 0, okay? And we find the H octave. But what is the problem or the semi-problem with this? This H here, let's stick it up. This H here is the same H here, the same H here. Okay? So this equation can be solved by H equals 0. Okay? You agree? If H equals 0, H equals 0 satisfies this equation, but again, we cannot use H equals 0 because we divide by H. Okay. So maybe these cancel. This is the epsilon of x minus h, and this is the epsilon of x plus h. And we don't know exactly what is the value of the function in x minus h and in x plus h, and maybe the same error would be, and maybe not. It's for us somehow random. But we can think that there are ranges, that these are give somehow a constant difference between them. And then in these ranges, this error, in the little range, this error will blow up when h goes down. Okay? And because of this, and this goes down when h goes down. So because of this, we ask when this equals to this. But again, when we do this calculation one time, it's not good because we don't really know if this cancels. We do this calculation many times in iterations in hope to find out. Okay, in hope. Okay, so that's the problem with what I've done now. So okay, I take an arbitrarily a small, very small number, h, for example, 10 to the minus 4, and calculate f at that point, x minus 10 to the minus 4, and calculate here, and make the difference between the errors, and divide by this, and find h, and hope that I find h close to the 10 minus 4. Okay? Maybe it will be 1.1 10 to the minus 4. So what do? I reassign this h here. Okay? Then I put now this h 1.1 10 to the minus 4. And again, I calculate this and let's say fix my h. In a hope that I will converge to some h that satisfies this equation in a very good way and at high precision or accuracy. Okay? So one calculation of this is not good. We have to do iterations with a hope. And that's why I again say you can drop that error. Okay. So here is a little problematic thing that you will have to know. When you have two numbers, one is much larger than the other, remember that the relative error in each number is 10 to the minus 7 of it, relative to it, yes? So when we add these two numbers, so if we have these two numbers and store them, they will be stored in the computer precisely. Okay? But when we add them, we get this. This number will be stored up to 10 to the minus 7 of it, so up to here. Okay? And then we lose this information. But this information is 10% from the original small number. Okay? It is 10 to the minus 7 from this number. Okay. But from this number, it is 10% from the smaller number. So if we add two numbers, one is much larger than the other, we lose information about the smaller one, and we will see a consequence of this in a bit. Okay, so this is a problem that you have to be aware of. Again, again, in this course, our point from this course is to use our mathematical knowledge in order to build algorithms in tricky ways sometimes, in order for the errors to be as small as we can. Okay, that's the point of our course. So we will see an example of the problem, this problem in a bit, but for now, let's let's see this example that thinks about the total error, and it's again a very, very basic and simple example. Let's say that we want to calculate this function in when the x is small or very, very small. So our problem again is that if the x is very, very small, we have the problem of overflow. And this function, you know that when we go to 0, it goes to what? When x goes to 0, it goes to what? 1. You can use a orbital, for example. So we want to tell the computer that if x is 0, then the function is 1, and else the function is like this. We want to tell him that, but because of the problem of underflow, we don't tell him if x is 0. We tell him that if x is under or smaller than some small value, for example here 10 to the minus 5, and else you can calculate this. And when we do that, let's focus on the borderline case around this 10 to the minus 5, and let's ask about the total error when we under that 10 to the minus 5 or above it. So if we are under the 10 to the minus 5, actually we've done a truncation, yes, because the function itself, we told him if x is smaller than the 10 of the minus 5, the answer is 1. This is a truncation because the f itself is 1 plus something. Okay, so the correction for that, or the error of the value of the function, or the value of f of x, it goes like x over 2, or the half of x, and it's bound. Yes, that's the bound. Maximum it will be x over 2. Again, that's because of Lagrange's theorem. And so our error here is the half of 10 to the minus 5. That's the truncation error. And the rounding error, I say here 0, but it's not true. It's the last digit also. The rounding error is 10 to the minus 7 here. And what happens when we look at x bigger than 10 to the minus 5? Here we'll see that the rounding error is larger than we think or we thought. Because we don't have a truncation error. Again, we assume that somehow the computer knows how to calculate this f of x, and now it wants to store it in that string of float or double float. Here we assume float. So when it stores e to the x, the exact value when x is 10 to the minus 5 is this, okay? And if we have a problem with that story, if there is an error, the error would be in the 7th digit, so it will be 1 here, okay? But now the function is e to the x minus 1. So we take minus 1 from the true value, or minus 1 from the estimated value or the approximated value, and we get and divide them by x, we get this. And now, when you take -1 from this and from this, you see that the difference now is 1% from the real value. So because we took -1. So here the rounding error, its propagation got me or gave me 1% of relative error, and that's large. Okay, so we can go to double float storing, and we can get 10 to the -10 instead of 10 to the -2, and it's the same calculation but with another numbers. Okay, so as you see, the round of error after only one calculation or 2 steps, 1 step or 2 steps, it got to be or it achieved to be 1%. That's big knowledge. So let's talk about this propagation, and again we are talking about basic things, simple things. So when we add 2 numbers, how does the error propagate in this process? It's only the addition of the 2 errors. Yes. So when I get the new value is the sum, the real sum, but added to it the 2 errors that were before. But there's a problem here when P is somehow near to -q. That's the problem that we have seen. Yes. Here, the number we added to it -1, so the P is -q or near to -q. And when we do this, there's the problem that now the relative error is large. Yes? If the P plus Q is near 0, the relative error would be large. Or in other words, when we subtract 2 close numbers, there is the problem of the relative error. So we have to be aware of that. And when we multiply 2 numbers, you know, we have not only the multiplication of the errors as error, but also the cross multiplication between errors and the real values summed. And now we can say that this is much smaller than this, but anyway, we can think about the relative error, and the relative error of multiplication is the sum of relative errors. Yes, you can see that. So that's the thing that good to be remembered. And again, we hope, of course, if our algorithm is stable, it's fantastic. But in real world or real calculations or computations, we don't have stable algorithms. We have slow algorithms, and that's fair enough or good enough. So what's slow? If the algorithm or the error goes linearly, grows linearly with the number of steps, how do we call this a slow growth, and it's good for us. If it goes like an exponent, if it goes exponentially with the number of steps, so it's a number, it's C multiplied by a number to the power of n, or more than n squared. So if it's a number to the power of n, that number, if it's bigger than 1, so that's not a good algorithm. Okay. Maybe it's the best we can do. Okay, but it's problematic because if we add steps, the arrow goes or wants to explode somehow or diverts. And if that number is smaller than 1, that's the stable algorithm. Usually we don't have these algorithms. but that's fantastic. That means that if you continue, you get much smaller exponential in your error. So we are good with linearly growing errors. And now for your homework, I will mention this thing. That's based on also the problem of summation or addition. Let's say that we want to find the roots of this equation, this quadratic equation. And we know, I told you that the roots of this quadratic equation are these two. So we know that if I call this one, this A, and this I call it B, and this I call it C, and then the roots are minus B plus minus. Yeah, you remember that. Okay, but here we have a very small root. Let's see how we get this root. This root will be gotten from here. Let's assume, forget this, assume that B is positive. If B is positive, for AC, let's see, C, A, 4, is much smaller than the B squared. So there will be that problem that we talked about, that when we make this subtraction between B squared and 4AC, we lose information about the 4AC. Not that we lose all the 4AC, but we lose some information about it. And then, anyway, this square root will be approximately what? B itself. I said suppose B is positive. B itself, and that's why the minus B plus B will be 0 or near to 0. Yes? So that's the small number. And if we can run away from this subtraction somehow, subtraction between a large number and a small number, when we calculate x2, I'm talking about x2, not x1. If we can run away from this calculation, it's better, and we'll see that it's better. Okay, so here is the first way. Here is the first way. I call A to be 1, B to be that number, C to be that number, and I know what are the true values of the. Huh?
Can you unmark the things of the contrast?
Now, yes. Good ideas. Thank you. And I know what's x1, the real value, and x2, the real value. And I only do the minus b plus minus the square root of b squared minus 1ac divided by 2a, but the a is 1, so it's good. And print the values. These are the roots that I find, and if you look here at the smaller root, you will see that it changes and this digit, yes?
Yes.
Yes, and this digit. So it's up to 10 to the minus 8 or 9. Okay? 8. So the accuracy here is up to 10 to the minus 8. And because of our mathematical knowledge of quadratic equations, we can take another way to calculate the x2. Again, I always want to calculate the bigger one in its magnitude, and the smaller one, if it's very small, I want to calculate it in another way, so that it is important for me if b is positive or negative, because the minus b plus minus square root, the square root of b squared minus 4ac is the absolute value of b. Okay, so I have to decide which which root is considered the bigger, dependent on the sign of b. And then I say that I know from high school or from this this simple definition, let's say, or simplification. I know that the sum of the two roots has to be minus b over a, and the product of them has to be c over a. I think they are called in high school Vieta formulas or Veta. Yes, he knows. Okay, so I know this, and if I don't know this, here's the proof. Therefore, I will calculate x1 by the minus b plus square root. This is the bigger. If p is positive, I will calculate x1 to be minus b minus the square, and if b is positive, minus b plus the square. So that's how I say that. Okay, and then the x2 I take it to be c over a over the x1. Okay. Okay, that's all because I know this thing. Yes.
This means that most of the calculations we like to do, we won't be able to just provide an unconditional calculation. We always have to, if you want to have a generic function, let's say calculates, like polynomial, right? We'll always have to, we'll always have to first check what the parameters are and then choose an order of operations in order to minimize the errors. There's no way to just calculate it with an set of errors. There's no one best solution.
Yes and no. The yes is with changing your sentence. I have to know some mathematical background. Here, the background is the solution itself. I agree with you. The background that I know here is the solution itself. Okay? But I don't have to know the solution. For example, here in quadratic equations, it's enough for me to know that c multiplied by a is much smaller than b in order square root of b, in order to know that I have to use, or it's better for me to use this way. Okay, so
I can do one check and then choose between two orders of operations.
yes, in this example, but anyway, in any way that you want to solve something numerically, you should know what your error is. So if I use that way, not a problem. I know that I can do a calculation as in a mathematical calculation and know that my error would be or will be up to 10 to the minus 7 or minus 8. I can do that without knowing the real answer or the exact answer. Or the exact value.
If I'm okay with a bigger error, I can have a simpler algorithm.
Yes.
If I want the minimal error, I will have more complex.
If you want the minimum, the most minimal error, so you have to make tricks based on what you know, and maybe you cannot prove that this is the minimum. Maybe after 10 years, someone gives us a better algorithm. But you know, there are algorithms that it is proved that there is no better for many problems.
But I'll have to branch anyway.
Yes. So for this example, when we calculate in this way, now the error is the relative error is up to the 10 to the minus 16. Okay, so we achieved or we added 7 orders of success, let's say. So in your homework, your homework, you will deal with some equations like this. And um, and you will deal also with what's called finite difference equations. There are equations like this. Let's get it bigger. There are equations like these, and they are called finite difference equations. What I will tell you now is nothing that only you can check in Google or Wikipedia to see how you can solve these equations. Analytically, it's based on some some guess, and you try this guess and make sure that it's good. And there's another way also. You know Fourier transform?
Oh, yeah.
Not yet. So there is a Z transform or discrete Fourier transform that we can make to these equations, and then they are simple algebraic equations. And we find the solution, and then we make the inverse a Z transform. Anyway, these are simple finite difference equations, and it's it's easy for you to solve them. That's what I can say. And here you will see in your homework how the errors propagate when you try to solve them numerically. So the first two questions are are theoretical, and then you have the programmatic part. And you will see how the error propagates and accumulates. That's a very good thing to see in your eyes when you try. And that's it for today. I see that maybe I'm too fast, maybe the recitations are too short, I don't know. And see if I will add questions to the recitations compared with what has done before. Okay, that's it. Any questions?
Upload.
They're already uploaded, yeah. Yeah.
Upload.